Welcome to Unit 6B Video Lesson 5. You actually don't have too much reading to go along with this video because we only have one topic, equation conversion. How do you go from rectangular to polar or polar to rectangular form with equations? Now we did this with coordinates in the last video, so we're going to be moving on to something that's slightly more complicated but uses the same idea. The main methods and facts to keep in mind. Number one, we have those exact same equations that we used before in order to go from r and theta to y and x, or y and x to r and theta. Same four equations, once again, not on your formula sheet. So you substituted these before, now we have to kind of create these equations in order to substitute. So you want to create a situation where you have x squared y squared, so you can substitute in r. Create r sine theta, so you can substitute y, etc. Now how do you create those situations where you can have that substitution? Well, for one, you can use your basic trig identities, especially the reciprocal identities, such as 1 over sine theta equals cosecant theta, and 1 over cosine theta equals secant theta. Another method we're going to be using is remembering that it is okay to just multiply both sides by r. It seems random, but if you're trying to get r squared here, to replace it with an x squared plus y squared, that's helpful. So it's random, it seems, to multiply both sides by r, but it is okay and it can be helpful. Another thing that seems a little bit random but is perfectly fine, and is actually something you learned before, is that it's okay to add the same number to both sides if it helps you create a perfect square trinomial. This is called completing the square, and you should have learned this in Algebra 1 and Algebra 2 when you were talking about trinomials and factoring and all of that with quadratics. So let's try a couple. Converting from rectangular to polar equations. Right now we have an x and a y. We want to change this into a polar equation of the form r equals some f at theta. So you want r by itself and theta to be your variable. We're going to use substitution first. 2 times, we know what x is equal to. X is equal to r cosine of theta, plus 3 times, we're going to substitute for y, r sine of theta, and that'll be equal to 6. From here, we want to get r by itself. That's our goal. So we have an r in both terms. It is a common factor. So I'm going to factor out an r from the first term and be left with 2 cosine theta. Factor out an r from the second term and be left with 3 sine of theta. And that's equal to 6. r is almost by itself. What do we have to do? Well, we're currently multiplying. It's time to divide. 6 divided by 2 cosine theta plus 3 sine theta. And you can't really simplify this any further, so that's your final answer. The second one is going to be a little bit more complex, because although we could just replace the x and the y with r cosine theta and r sine theta, right now that x is in the middle of something that's being squared. I'd much rather square this than square r cosine theta minus 3. So we're going to start by squaring this. Remember to FOIL. X squared minus 6x plus 9, and then you add your y squared, and that's equal to 9. From here, you should notice that you have some other possibility for substitution. You have an x squared and a y squared. You should know that x squared plus y squared is the same as r squared. Minus 6, oh, I still have another x. I don't want x, I want r and theta. So I substitute in r cosine theta. Plus 9 equals 9. Well, r by itself, we need to get r by itself. For first things, we want to make it so we have a 0 on this side, so you can subtract 9 from both sides and end up with r squared minus 6r cosine theta equals 0. Because when we have a quadratic, you always want 0 on one side. From here, we could try to factor, but it's a binomial, not a trinomial, so we don't even have to do the hard factoring. We have an r squared and an r. R is a common factor once again. So factor out your r, and you're left with r minus 6 cosine theta, and each of those are equal to 0. Once you have two factors equal to 0, you can set each one equal to 0. This one, done, r is by itself. How do you get r by itself? Just add. So we have two equations, this or that. So we have two equations that represent our original, which makes sense because our original wasn't actually a function. It was a relation, but it wasn't a function because this is a circle centered at 3, 0 with a radius of 3. Remember, this is r squared, and then the things you subtract from x and y are the center. It's just like with those spheres that we talked about a few videos ago. Just thought I'd mention it. Alright, so that's how we do converting from rectangular to polar. And those are kind of the two main types of equations you're going to be seeing. Converting from polar to rectangular, we have two potential goals. Before, we always had to get the r by itself. Now, if possible, we can get the y by itself and just do y equals f of x. But actually, very frequently, we're going to try and get this into a relation form, not a function form, of a circle. So h, k, and r would be numbers. You're going to replace those with numbers, and x and y are still going to be your only variables. So let's do the first one. We want to convert r equals 4 cosine theta into a rectangular equation, which means instead of r, we want x and y, not r and theta. Well, right now, we have an r by itself, and we have a cosine theta by itself. To change r over, it would need to be with the cosine theta or as an r squared, if you remember our two equations. R squared equals x squared plus y squared, or we also have the r sine theta, and that's going to be your y, or your x was r cosine theta. You never have anything where the r is just by itself. So let's make it so the r isn't by itself anymore. We have the option of either moving it over to the cosine, but that would make it cosine divided by r, and that doesn't work, or just adding another r. I'm going to multiply both sides by r. Hey, that gets me an r squared. That helps here. And if I multiply this side by r, I get 4r cosine theta. Hey, that helps me by getting this piece that I can replace with x. So x squared plus y squared equals 4 times r cosine theta, which is replaced with x. Hey, now I have the right variables, I just need to get it in the right format. Well, I have a y squared. So that tells me I'm probably going to prefer the circles format instead of just getting y by itself. So that means I need to figure out x minus something squared and y minus something squared. Let's start by getting all of the variables on one side. X squared minus 4x plus y equals 0. Y squared. Alright, I'm closer, but I'm supposed to have an x minus something squared. I need to make this into a perfect square trinomial so I can say that it is some binomial squared. So how do I do that? I complete the square. That means I am creating a perfect square trinomial. I need to figure out what number I would add to these two terms to create a perfect square trinomial. And then if I'm adding it to one side, I'm going to have to add that number to both sides. Now let's remember what a perfect square trinomial looks like. Let's do the most simple. That's supposed to be a square. Most simple form of that. Since in this case our a is just 1, we're going to talk about x plus some number b if we're squaring that binomial. We end up with x squared plus 2bx, where this is the coefficient of your x term, plus b squared. So this is the simplest form if you only had one variable, not two, but that's the basic idea. So 2b is the coefficient of our x. In this case, that's negative 4, which means our b in this case should have been negative 2 in this problem. So that squared should be the thing we're adding to create our perfect square trinomial. Negative 2 squared is 4. So I'm going to add 4 to both sides. From here, I can factor this. I know it's a perfect square trinomial where b is negative 2. That is x minus 2 squared plus y squared equals 0 plus 4, which is 4. And that's your final answer. That is of the circular format. Last example before I let you go. We're going to convert r equals 4 secant theta to a rectangular equation. Now this looks, it's secant, oh no, it's going to be so much harder, and we had to do all that like perfect square, completing the square thing, oh no. Well, as long as we remember that secant is the reciprocal of cosine, it's not so bad. We're going to start with changing that to 1 over cosine. So 4 times 1 over cosine is 4 over cosine theta. And now we're going to go back to thinking through which of these we need to use. Once again, our r is by itself. We need either r with sine, well, we don't have any sine in this case, or r squared, like we used last time, or r times cosine theta. Well, if we did the same thing as we did before, multiply both sides by r, we'd get an r squared, but over here we'd get 4r over cosine theta. And that doesn't get us the second piece that we replaced over here. So let's try the other version. Let's try and just move the cosine to the r. Because the cosine is in the denominator, when we multiply both sides by cosine, our r is multiplied by cosine. We didn't have that in our last problem. So we end up with r cosine theta equals, these cancel out, 4. Hey! R cosine theta can be replaced with x. So even though it looked more complicated because it had a secant, it ended up taking much less time as long as you remembered to change your secant to 1 over cosine and just multiply both sides by cosine. Alright, this is a short one, right? All done. We'll practice more of these tomorrow. Have a good night.